In one of the earlier episodes, we talked about the general nature of various kinds of ore deposits and their classification. Today, I have chosen three related processes. All three of them are related to magmatic activity. The title of the lesson is Magmatic concentration deposits, hydrothermal deposits and skarns. These three important processes come under the category of related to magma. However, magmatic concentration, hydrothermal solutions and deposits and skarns are the direct result of magmatic activity. Magma supplies heat, energy, ore elements and even water. Though water and ore elements could have other sources too. A large number of ore deposits owe their origin due to these three somewhat related processes. The lesson will be discussed under the following heads. We will begin with magmatic concentration, deposits, magmatic deposits and rock associations. Thirdly, we will deal with hydrothermal solutions, deposits and associated alterations. Then we will come to cavity filling and replacement deposits, and finally we will come to skarns. Sources of all metals is ultimately magma. When hot and under pressure, elements remain in solution, but sooner or later, with reduction of pressure and temperature, crystallization begins. Fractional crystallization will separate ore minerals and common rock forming minerals. Depending upon their temperature of crystallization, and early formed minerals may incorporate certain elements. Early in the crystallization history of this magma, if original concentration was more than normal, these elements like chromium may form their own minerals as oxides. These crystals, being heavier, will settle down with other common minerals and are referred to as early magmatic deposits. These accumulations, particularly in layered intrusions, make rich deposits of chromite, magnetite, ilmenite and also platinum. Perhaps one of the best example is chromite layers of Bushveld complex of South Africa. Sometimes early formed minerals instead of forming layers, gets sprinkled throughout the body of the magmatic rock, forming magmatic disseminations. Diamonds in the rock kimberlite and lamproite come under this category. All the primary diamonds deposits round the world, including the one at Panna in Madhya Pradesh, are of this type. Liquid immiscibility, as one finds in an oil water mix, can also separate sulphide portions from the rest of the magma. PowerPoint 1 illustrates examples of magmatic concentration and dissemination deposits. Ore deposits are also found towards the end stages of crystallization, say when 90% of the magma is solidified. These are called late magmatic deposits. In a layman's language, these are deposits which are formed from the leftovers in what we call residual melts. Residual melts may form minerals and get accumulated in the parent magmatic rock, or under pressure from the volatiles get injected through an outlet into other rocks. The same will happen should sulphide phase and silicate phase become immiscible and can segregate to form a mineral deposit, or may also get injected. Thus, late magmatic deposits can be of four types. 1. Residual liquid segregation, for example, titanomagnetite and platinum deposits of Bushveld complex, South Africa. 2. Residual liquid injection. The best examples are magmatic pegmatites from all over the world, which are storehouses for rare ores and minerals. 3. Immiscible liquid segregation, like sulphide deposit of Insizwa intrusion, South Africa. And lastly, immiscible liquid and injection. Association of mineral deposits with specific rock types is a very useful theme. This goes on to prove a very close link between petrology and economic geology. Once we have grasped this fact, we will not look for a right thing in the wrong place, and this is the basis for all kinds of mineral exploration. In general, for most of the magmatic deposits, the host rocks are mafic and ultramafic bodies, being specific all over the world. Following ore deposits, magmatic rock types association is very well recognized. Primary diamond with kimberlite and lamproite, chromite, magnetite, platinum and iron with peridotite, dunite and gabbros. Titanium ores with magnetite, with gabbro and anorthosites. Nickel copper sulfide with norite and corundum with nepheline cyanite. Beryl, lepidolite, tin, tungsten and polysite, which is an ore of cesium, they are with pegmatite. These are perhaps the most common group of metallic deposits, including those of copper, zinc, lead, mercury and silver, and also gold and tungsten. As the name indicates, these ores were transported by hot water fluids. The temperature may range between greater than 500 degrees centigrade and pressure 1 to 3 kilobars. Their major constituents being sodium, potassium, calcium and chlorine, while several minor and trace elements include copper, lead, zinc, magnesium, boron, sulfur, tin, molybdenum, gold, silver, as also carbon dioxide and SO4. Source of heat and the driving force undoubtedly is the magma chamber. Metals could be either from the magma or the remobilized metals contents of the rocks in the surrounding. Fluids, mostly water, may be of diverse origin, including juvenile, that is dissolved in magma, connate, that is trapped in the sedimentary rocks. Since their deposition, it could be meteoric, that is from the surface, it could also be from sea or even metamorphic water. One of the best display of mineral rich hydrothermal fluids, which we call brines, emanating from the depths of the ocean floor along the mid-oceanic ridges, has been through what we call black smokers and white smokers, as also we find near the Salton Sea in California and the Red Sea area, from which precipitation of gangue and ore minerals from hydrothermal fluids take place, quite often aided by bacterial activity in fractures, faults, breccias, openings and other spaces, simply by open space filling called cavity filling, or by replacement, thus giving two major classes of hydrothermal deposits: cavity filling deposits and replacement deposits. Depending upon the pressure temperature range of their deposition or replacement, there are 5 types of hydrothermal deposits, namely hypothermal, where the temperature range is more than 400 degrees centigrade and the depth is far great; mesothermal, between 240 and 500 degrees centigrade, moderate depth. Then we have epithermal, less than 200 degrees centigrade at shallow depth; telethermal, where pressure and temperatures both are low; and xenothermal, which are close to surface but at elevated temperature. A list of minerals indicating temperature pressure conditions of the hydrothermal deposits is as follows. Under the high temperature and great depth, we have wolframite, which is iron tungsten oxide, cassiterite and magnetite, also chalcopyrite, molybdenite. At medium temperature and pressure, the list of minerals include chalcopyrite, pyrite, galena, sphalerite. At a low temperature range and shallow depth, the mineralogy includes argentite, pyrite and cinnabar, as also stibnite. During the process of hydrothermal ore deposition, alteration of the country rock is a characteristic and useful feature, especially for mineral prospecting. It will depend upon both the nature of hydrothermal solutions and the nature of the host rock. Following types of hydrothermal alterations are well recognized. Number 1, sericitization. It refers to the development of fine grained white mica called sericite and quartz, and results from the breaking down of orthoclase feldspar to sericite and quartz. It is also known as potassic alteration. The second is silicification. It is a very common type of alteration resulting due to the introduction of quartz and cryptocrystalline silica, mostly opal and cherts. Third is dolomitization. It refers to the conversion of pure calcium carbonate host rock into dolomite with the introduction of magnesium from the mineralizing solutions by replacing calcium. Next is the argillic alteration. This is also a very common type of alteration and refers to development of clay minerals, namely kaolinite and mormellinite. It is extremely common in disseminated type of ore deposits, for example, porphyry copper deposits. And the last alteration is known as porphyritic alteration, represented by the development of green color produced by minerals like chlorite, epidote, chert and also calcite in the host rock. The country rock, which may be of any origin, is seldom without openings. These openings or cavities may be a depositional feature like pores of a sandstone or vesicles of a volcanic rock, or might have been produced in the rock due to tectonic activity or other factors after the formation of rock. These are called induced cavities. These original or induced openings become the favorable site for the deposition of hydrothermal fluids. Among all the processes of ore formation, this happens to be the most common type of mineral deposition and is responsible for a large number of deposits now being mined. The process of cavity filling is favored more at low pressure, that is shallow depth, and low temperature, that is less than 300 degrees centigrade. Thus, most of the deposits of the epithermal category will be of the cavity filling type. The second way involves chemical interaction between hydrothermal fluids and the country rock, whereby one or more of the earlier formed minerals of the country rock are replaced by the newly formed ore element or elements, often retaining the old structure to the very detail. The ore element content in a way is the gift of the hydrothermal fluids to the previous mineralogy of the country rock, and both together constituting the newly formed replacement deposit. The process of replacement is more favorable at high temperature and high pressure, and it should be obvious that is the way of ore formation will be more. Cavity filling in the rock is analogous to a dentist filling a tooth cavity and is by far the most common process of ore formation. Layers after layers of minerals in a symmetrical way making a comb structure. Several types of cavity fill deposits have been recognized, as will be seen in PowerPoint 3. Igneous and sedimentary rocks will have different types of openings which will become sites for mineral deposition. To name few: fissure veins, shear zone, stockworks, saddle reef, ladder veins, breccia fillings, pore spaces, vesicular fillings are some of these.